All right, so welcome to our second little chapter here. So I'm sure we've kind of already talked, but I think one of the issues that we were kind of having last chapter, even though you guys did a nice job with everything, is when I give you an equation and we're talking about domain or range or stuff like that, it is a huge help if you have a decent idea of what that graph looks like in your head already. Okay, now all the functions that we're going to talk about, you've seen at some point in your life, either in Algebra 1 or Algebra 2, somewhere in there. But you guys have not mastered them yet, and that's okay because you weren't expected to before. But we really need to master these functions so that in calculus, especially, when you're doing all these different actions and algebraic functions with these equations, you already know what the graphs look like in your head. Okay, so we got to talk about any function that you might run into. So the first thing we're going to do is we're going to talk about what are called our parent functions. Okay, so our parent functions, these are the basic functions that we're going to transform into basically an infinite amount of other functions. Okay, but you have to know these parent functions by heart. You got to know what they look like. You have to know key features. You cannot be grabbing a calculator and typing stuff in. You can't be making a table every single time. These parent functions you just got to know. Okay, and then in the next couple of days, we're going to learn how to transform these parent functions into more complex versions of themselves. But if you know the parent functions and you know the rules for transforming functions, then you can graph thousands and thousands of different graphs without even having memorized what they all look like, because you know the parent functions that we're going to talk about and you know the rules for transforming them. Okay, so we have about 7 parent functions that you just got to know what they look like. All right, so the first parent function is nice and easy. F of x equals x. All right, so hopefully you kind of already know what this one looks like. So this is a linear function. So when I say f of x equals x, you should already know what that looks like. This is a linear function with a slope of 1 because we have our imaginary 1 out in front. There's nothing out after the x. There's no plus b or anything like that. So my y-intercept is 0. So if I'm going to graph this, this would be a linear function. Slope of 1 goes through the origin. And so there's our first parent function. Okay? So f of x equals x. So nothing too crazy there, but we're just starting with the most basics. So anytime you see something, this has a degree of 1 up there. This is really like x to the first. So anytime we have a function with a degree of 1, then we know that's going to be some sort of linear function there. All right, so that one's pretty easy. Let's look at the second one here. So the second one that I want to talk about is f of x equals x squared. Okay, now we're going to mainly focus on x squared, but something that I want you to keep in mind and make a little note here, that if we have x to any even exponent, these functions are going to have the same general shape. Okay, and we'll talk about how they're going to be different in a second. But if you have like x to the 4th or x to the 6th or x to the 8th, they're all going to kind of take the same parabolic shape that we'll see here in a second. All right. So if you think about, if we make a quick table here, we'll probably make a lot of tables today. So on my table, if I just throw in a couple negatives, a couple positives, 0 is always a good idea. So if I take a look, if I plug these in, 9, 4, 1, 0, 1, 4, 9. So here's my table for x squared. Okay. Now something that you should notice here that you already know about is that all of my outputs here are positive. Okay. And why is that? That's because I'm taking my inputs and I'm squaring it. Squaring it just means I'm multiplying by itself. And anytime I take a negative number and multiply it by another negative, that's positive. Anytime I take a positive number and multiply by another positive, that's also positive. And so that's why we get all of our outputs are positive. Okay? So when I go to graph this, I don't need to make a perfect graph today. I'll just go ahead and throw a few points. So negative 1, 1, negative 2, 4. Oops. That was not my best effort there, but we get the idea. There's my parent function. So this is f of x equals x squared. Okay, so that one you probably already knew. Now what about like x to the fourth? How's that going to be different? Well, if you think about it, if I, instead of taking this number and multiplying by itself 2 times, if I multiply by itself 4 times, it's still going to have this same general U shape. It's just going to get bigger faster. Okay, so you don't have to put this in your notes if you don't want to make them messy, but x to the fourth would maybe look something like this. So it'd just be kind of like a parabola, but it's going to be much steeper because it's getting much bigger, much faster. Okay, but if we don't have our axes labeled like super cleanly, x to the x squared, x to the second, and x to the fourth, those are going to look about the same. Okay, so there's our second parent function. All right, so our third parent function, you might be able to guess it. We had x to the first, x to the second. So our next parent function is going to be x to the third. Okay, so if we look at x to the third, again, this might be one that you recognize from last year. But if I make just a quick table, negative 2, negative 1, 0, 1, 2. So what am I doing when I'm cubing a number? I'm cubing a number, I'm taking that number and multiplying it by itself 3 times. So negative 2 cubed is negative 8. Negative 1 cubed is negative 1, 0, 1, 8. Okay? So this is going to be different than our quadratics because we can have negative outputs. Okay? So if we talk about domain and range, if you look back at your quadratic, you notice that your range was anything greater than or equal to 0. So 0 was okay, and everything that was positive was okay. But there's no negative numbers in your range. But we can see that that's not the case here. Okay? So in our cubic function, if I plot a couple points here, so negative 1, negative 1, negative 2, negative 8. So it plots points. It still goes through the origin there. And so we get something that looks like this. Okay? So my domain is all real numbers. My range is all real numbers. And we get this S, kind of like this stretched out S looking curve. Okay? So this is my cubic functions. And kind of similarly with what we talked to about x squared, maybe make a note up here. This is the general shape of x to any odd exponent. Okay? So x to the third, x to the seventh, x to the fifth, x to the ninth. I guess odd, but not 1, obviously, because x to the first I just beat my. Okay? But this is the general trend of x to any odd power. All right, now key features here, goes through the origin. We have all the negatives and all the positives in both my domain and my range. Okay? All right. Now the next one, we did x to the first, we did x to the second, we did x to the third, but we kind of already talked about x to the fourth, right? Because we said all even exponents are going to kind of look like a quadratic. All odd exponents are going to kind of look like our cubic function here. So what's our next one? Well, for the next one, let's do, I'm going to put b to the x. All right? So some number, I'll put a little note here, b is a constant. So a constant, that just means it's just a number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So some number to the x power. All right, so these are exponential functions. So you probably already knew that these are my exponential functions. B, we have some different names for it that we'll talk about when we jump into our exponential chapter. Could be a growth factor. stuff like that. Okay? But in this case, it's just a number like 2 to the x. All right? So let's make a little table here just to kind of get a sense of what's happening. And for my table, I'm going to have my b value be 2. So I'm going to graph 2 to the x. All right? And just like normal, I'm going to throw in some negatives. So -2, -1, 0, 1, 2. So let's talk about our exponent here. So if I plug in -2, so 2 to the negative second power. So what is happening here if I have a negative exponent? Well, you guys probably remember if I have a negative exponent, what that means is I really have 1 over 2 to the positive second power. So anytime we have that negative exponent, really what that's saying is take the reciprocal of that. Okay? So instead of this being like 2 over 1, now it's 1 over 2. So we're taking the reciprocal. All right, so 2 to the negative second is the same as 1 over 2 squared, which would be 1/4. All right, if I had 2 to the negative first, take the reciprocal, that'd be 1 over 2 to the first, or just 1 over 2. Now, what about 0? So if I plug in 0, 2 to the 0, so 2 to the 0, well, you might remember anything to the 0 power is 1. Okay? And we can talk more about that some other time. It's kind of a counterintuitive thing. Like, what is 2 squared? That means 2 times 2. 2 cubed, that'd be 2 times 2 times 2. 2 to the 4th, that'd be 2 times 2 times 2 times 2. So how does 2 to the 0 equal 1? What does that mean? I don't know. We'll talk about it some other day. But for now, we'll just go with what we've been told in our algebra classes. Anything to the 0 power is 1. And then 2 to the first is 2. 2 squared is 4. Okay, so now we have some values that we can throw on our graph. So what is going on here? So we have a y-intercept of 1. And then as these x values get more and more negative, are we ever going to have any negative values down here? Nope, I don't think so. Because we found up here, a negative exponent doesn't actually give us a negative output. All it does is it takes the reciprocal of that. And so what happens is this graph is going to get closer and closer to the x-axis, but it's never going to touch it. Okay? And then once I get past my y-axis, this graph is growing exponentially. It's getting bigger and bigger and bigger, faster and faster and faster. Okay? Now, is this ever going to equal 0? Is it ever going to touch? Well, it doesn't look like it. How could we check? So something we could do to check is we could try to brainstorm about this. Is my output ever going to be equal to 0? So 2 to what power is equal to 0? And we said 2 to the 0 is 1. We said all of our negative numbers just give me a reciprocal. All of my positive numbers are just going to make this bigger, bigger, bigger. And so there's no way that we can ever have 2 to the x equal to 0. So it's never going to touch there. Okay? So I'm actually going to pause. I'm going to make a couple notes real quick. So with my exponential functions, my y-intercept is equal to 1. And what do we call it when it's kind of flattening out? Kind of like an asymptote here, I guess, right? A horizontal asymptote. So we could say horizontal asymptote at 0, or I think I might just say flattens out at y equals 0. Okay, so we have a y-intercept of 1, and it flattens out at y equals 0. So it's never going to touch y equals 0, but it gets as close as it can. Okay, so those are our first 4 pair functions. We got to make sure that we have these memorized. So if I say, hey, graph 3 to the x, 4 to the x, you got to be able to do that. Okay, and before we end, that's a good question by myself. What would this look like if it was 4 to the x, 5 to the x, or 6 to the x? Well, it's going to basically look very, very similar because let's say we were graphing 5 to the x. Well, what's the y-intercept? Well, 5 to the 0 is still 1. And it's just going to get bigger faster. Okay?